So welcome everyone. Welcome back to power system classes. So the last class, we were starting the power system analysis, and the first part of the power system analysis is basically the surges in an electrical power system, right? So we were looking at the surges part, okay? Surges in power system. So yesterday I have explained that when should we consider the the importance of surges, when should we consider, and so from the frequency we divide our circuit into something known as lumped parameter model, something like a distributed parameter. So when will this lumped parameter model is valid? When the lambda or the wavelength of our signal is very much greater than 10 times the L. Okay, that is lambda is greater than 10 times the or 20 times. Some people say it's 20 times. Then actually, we can consider the lumped parameter model. Otherwise, we have to stick with our distributed parameter model. Okay, we have to stick with our distributed parameter model. Okay, so when lambda is less than 10 times L, okay, then we have to go with distributed parameter model. So in lumped parameter model, we will get something known as algebraic equations, right? So something like KVL, KCL, Ohm's law. These are algebraic equations, right? So V equal to IR, sigma V equal to 0, sigma I equal to 0. Okay. So we can solve all these algebraic equations, and from this actually we can find the different voltages and potentials at different point. But that is not applicable here because here the things are not lumped. Everything is actually distributed. So you have to consider differential equations. Or in other way we can say partial differential equation. Okay. And integral equations. So if someone asks you which is more valid or which is a more general case, then you have to say this is more general case. And this lumped parameter model is a manifestation of this distributed parameter model at this particular condition. Okay. Since we are actually in our power, in our power frequency, the wavelength is very, very, very small, very, very, very large. That's why actually we are not worrying about dividing and distributed. But at very high frequencies, then still we have to consider distributed system. Then only our analysis will be correct. Okay. So for example, if you say something like this, okay. So I hope everyone has studied electrical machines, the transformer. Okay. So what is the equivalent circuit of our transformer? What we study in our normal B.Tech level is this, right? Right. But normally nobody will say that this is valid only for 50 hertz, right? So the equivalent circuit, what we normally study in our electrical machines class, is only valid for 50 hertz. So, if you want to look at a very high frequency, model, or the how a transformer actually works when a surge comes to it, it is quite different. Okay, the equivalent circuit is something like this. Okay, so infinite number of systems are there. Then there is something I'll say. This capacitance. Then there is something else, a shunt. So a transformer will be actually looks like this. This is the current circuit. And you can ask what happens to this one. Okay, core loss and the copper loss. So where is this core loss and copper loss happening? This is happening inside the core, right? That is what is known as the core loss. Sorry, the core loss and the magnetization part. But what happens is that at very high frequency, there will be very huge eddy currents. Okay. So none of the flux actually penetrate into the core. So that effect of these losses will be very, very, very small. Okay. So actually we can neglect this, but we have to include all the capacitance. Okay. And at very high frequency, there will be very high skin effect. So we have to consider all the resistance also here. So this is how the circuit manifests into a very high frequency thing. So for all the machines, like, if you think about motors, if you think about generators, we study only the, like, static or quasi-static equivalent circuit. But for transients, we have to look at something much important than the static or quasi-static. So these things are very important for your interview. They might ask, actually, is this circuit valid for all the frequencies? Then you have to say, no, the circuit is not valid for all the frequency. This circuit is valid only for a very low frequency, like 50 hertz per hertz, 0 hertz, or like our power frequency. At very high frequency, we have to consider the capacitance, intercapacitance between the turns, and capacitor with respect to the tank also. So all the capacitance we have to include. Okay. So that's the difference between a lump parameter model and a distributed parameter. In a lump parameter model, the things are actually fixed because this is the primary and this is the secondary. In a distributed parameter model, there will be infinite number of sections. Okay. Infinite number of sections in a distributed parameter. So this is very important. In a lump parameter model, number of sections are always fixed. But in a distributed parameter model, there will be infinite number of sections. So sections, that's why actually we get a something on say differential equation. Okay. So this differential equation is valid at each and every point of the winding. Okay. So that means we can actually find a point form solution. Okay. At this particular point, this equation is valid, and at this particular point, this equation is valid, and that equation is valid for all the points and all the times. Okay. So something like dou square v by dou x square equal to 1 by v square dou square v by dou t square. Something like that. So this equation is valid at all x in the transmission line. Okay. Wherever there is an x point is there, this is valid. And it is valid for all the t also. For every time this equation is valid. Okay. That's why this represents a point form in the solution. So for all the points, this is valid. Okay. So if you consider this point, this is valid, this point valid. But the value of x will be different. That's all. So something like, if you solve a Algebraic equation, at some point we know the solution, then actually we'll extend it to each and every point. Okay. So similarly, we have to find the value of v at each and every point at each and every time. So something like this will be. So if you find the voltage distribution across the line, there will be actually something like this for some time. Then at t equal to 0, it will be like this. Then t equal to 2t, it will be something like this. Then 3t, it will be something like this. We have to find the solution of this particular PD to find the voltage distribution across the line at a particular point at a particular time. Okay, so this is time dependent. But here, this is time independent. That is the main difference. In lump parameter model, things are actually time, like, the voltage actually is not at a point, is like, it's not exactly a function of time. Okay, that is always fixed. This voltage is actually fixed. Here the voltage varies with respect to time. Okay, so these are the basic difference between a lump parameter model and distributed parameter model. So this is very important. Like, people might ask what is the basic difference. In most of the interviews, they will ask what is the basic difference between a lump parameter model and a distributed parameter. You should have a thorough understanding about this. So that's why in long transmission line, we are actually considering this particular distributed model. But for short transmission line, we are actually going back to the lump model. Okay, this is the thing. Okay. Now let us consider something else, a transmission line. Okay, because all the transients are actually coming through this transmission line, right? So the first thing they see is actually the transformer, because transformer will kill almost all the transients. Then it will pass through the transformer to the power system. So for the time being, actually we we look at the transient behavior of transmission line. Transient behavior of transmission. assume that some surge actually comes here, and this travels to this. Okay, this surge, you can say some E, and this actually traveling to this direction. Okay, so each and every transmission line will be actually, if you check the other end of the transmission line, each and every transmission line will have some kind of a, like, what to say, some things actually will be given at this particular end. Okay, so this particular thing is known as the termination. Okay, so a transmission line can be terminated with a capacitor. Like, if it is a transformer, if it is connecting a transformer, then it is almost like an inductor. It can be either a resistor. So many things can be actually come in this particular termination. Okay, so this is very important. So then, what is the, like, if a current actually flows through a wire, the current actually flows through a wire. So what is the opposition force in the wire? That is basically the resistance. It's basically the resistance. But for the transmission line, if you think the things are actually, like, the transmission line is actually made up of those materials which are having very high resistivity, right? Sorry, conductivity, right? So that means the resistance effect will be actually negligible. But how a transient actually moves from one place to another, that is basically happening through the electromagnetic wave. Okay, so like, if you check, like, this, like, so the inductor will charge, so that charge actually gives to the capacitor, and the capacitor will discharge, that will be given to the inductor, that will be actually given to this capacitor, like this. So there is some kind of an objection due to this charging and discharge to the traveling of the charge. It cannot instantaneously pass through the this one. Okay, so that is basically something known as surge impedance. That is root of L by C. Okay. So inductance per unit length divided by capacitance per unit length. So this is almost remains a constant for each and every transformer, like, sorry, transmission line. Like most of the transmission line cables, so it will nearly, it is 50 ohms. Okay, like, that's how we actually designed it, 50, 60, 120, like that. Okay, so this is very important. So if I check here, this will be actually 50 ohms. Okay, so something having 120 ohms is also there. Okay, so like this. So the root of L by C is the surge impedance of the line, and this is independent of the length. This is independent of, because surge impedance is constant throughout the length. Because for 1 meter surge impedance is Z0, what will be surge impedance for 2 meter? That is again actually Z0, because this inductor and capacitor is per unit length, right? So length and length are cancelled, so it is independent of this particular. Okay, so assume that there is actually a surge, okay, surge of voltage E. This is coming through a transmission line, and we have some kind of a termination here. So if you check, every transmission line is characterized by something known as a surge impedance Z0 and its delay time tau. Okay, so each and every transmission line is characterized by its surge impedance Z0 and the delay time tau. Okay, these are very important things. And this is something known as a terminating resistance, that is basically ZL. Okay, so these are very important. Now we can check this. So I will draw the figure again here. This is a surge voltage E going through a transmission line. It's at 0. Then actually there is something outside. Terminating resistance is at that. This is basically is at 0. Okay. So surge is actually coming here. So each transmission line is characterized by its characteristics impedance or surge impedance is at 0, and the time for travel, time for one travel, that is basically tau. Okay. So if you check here, what happen is, like, if a wave come here, a part of the wave get reflected at this end, and a part of the wave actually flows through this one. Okay, So that reflection happening with a particular constant known as a reflection constant. Okay, reflection coefficient. That is what we actually represent this by something known as a gamma. So gamma is basically ZL minus Z0 divided by ZL plus Z0. Basically gamma L, okay, at the load side. So now the transmission coefficient that is actually happening here, this is basically reflection coefficient. The transmission coefficient is 1 plus gamma L. Right. If we check here, assume this is 1 is coming here, gamma is going here. So what is the voltage at this particular point? That is the sum of these two. This 1 plus gamma, that should actually go here. Okay. So 1 plus gamma L, that is 2 ZL divided by ZL plus Z0. Right. So this is basically known as the transmission coefficient. So if some k unit of surge is coming here, then gamma L into k actually goes back at this particular reflected position and other actually went through it. Okay. So now we can check some different terminations and what is gamma L. So what is basically open circuit? Okay. So what happens if an open circuit happens? So that is basically ZL will be now infinity, right? Because on open circuit the impedance will be actually infinity, right? So that is gamma L is basically 1. So what happens in short circuit? Okay, these are for voltages. Okay, so current just change the sign, that's all. These are for voltages. So what is basically happening in short circuit? Short circuit means this is basically 0, right? So that is minus 1. All right. Now we can check about what happens if matched what happens if ZL equal to Z0, something known as a match line. We give the termination ZL which is equal to the surge impedance of the line. So what happens is gamma L which is ZL equal to Z0, then gamma L is basically how much? 0, right? Right. So here we can write the transmission coefficient also. That is basically 1 plus gamma L. This is 2. This is 0. Right. 1. Right. So that means even if a surge comes here, right? So assume that something like this. We have some surge. Okay. These kind of things are very important for measurement of high voltages. Okay. So assume that we have to measure something like 30 kilovolt, very high voltage, very high frequency signal. Then we connect through a cable. You can see a cable for connecting to CRO. This is actually connected to CRO. Right. So what is happening here is if we actually this is having some kind of an impedance of Z0. Okay. If we give surge is actually some 1 kilovolt, and if there is no termination, what is happening is this 1 kilovolt will become double here, and the CRO will record 2 kilovolt. Right. That means there is a measurement error is there. So what if we connect a resistance, a termination resistance in CRO? Okay. Or the termination resistance equal to the surge impedance of the cable. Then what is the transmission coefficient? That is 1, right? So whatever is coming here, actually it will be actually going to the CRO. Okay. So, but this 1 kilovolt is very large, CRO might burn off. Like we will actually use some kind of potential divider to connect to the CRO. Okay. There will be some kind of a potential divider is there. So after the potential divider only we will actually give to CROs. Okay. So if you check here, this 1 kilovolt actually comes here, and this termination resistance is basically Z0 equal to ZL. Then what is transmitted to CRO is basically 1, right? So the exact thing will be actually measured by the CRO. So that's why we have to terminate for measurement of very high surges. What we have to do is we have to terminate our cable with its own surge impedance. Okay, that's basically known as a matched line. As a matched line. So we have to do something known as a matched line. So this is very important. Okay. So you should remember this because most of the people make mistakes here. So while we do some practical measurement, what happens is we actually forgets to put the matching kind of a thing. Okay. So Sierra will actually give you a wrong value of the thing. Okay. So you can actually write all these things, and we will continue after this. Okay. Just write all these things. So these kind of questions are very important for the interview. Okay. So why should we terminate this one? Okay. All these things you have to listen carefully, and you have to give the answers very correctly by drawing all the pictures or something like this. So we can actually, they will understand, you know the basics. Okay. Okay. I hope you understood the things. We can go actually forward. Now we can check other thing, like some kind of a surge is here, and there is a transmission line of Z0. Then what if we connect a capacitor? Okay. So how will the capacitor get charged or discharged? Okay. So that's a very important part, because these kind of things actually for testing of insulator and all, we have to give very large current through a, or an voltage through a coil, through a transmission line cable to the insulator. Okay. So this is actually, you can consider this as an insulator. So the current has to pass through, the voltage actually we have to give for testing and all this. So these type of things are very important. Okay, like for practical applications. So how a surge actually sees a capacitor. Okay. So here what we have to use is, we have to use something known as Thevenin model. Okay. So how a Thevenin model works? So for finding the Thevenin model, so we have to just remove the load from here. Then look at the voltage actually what this position sees. Okay. So if you remove the load, what this sees is, actually you can think about it. So what if we actually make this open circuit, right? What if we make this open circuit? So that means if you make this open circuit and look at here, the first instant what we see is actually 2E, right? Because this is basically an open circuit. So open circuit, what is the voltage actually C by at this particular point will be the transmitted, what is transmitted after the reflection, right? So reflection coefficient is basically 1. So transmission coefficient is basically 2. That means we see actually 2E. So that means if a person looks at this particular point, the voltage he sees is basically 2E. That will be the Thevenin voltage, 2E. Then what is the impedance? The impedance actually, if you short circuit this and change the impedance, that will be Z0. So this will be the model for this particular port. So then we can connect the load. Now actually we can find the voltage across this particular capacitor. So that will be in S domain 2 by S into 1 by Cs divided by Z0 plus 1 by Cs. Right. So if we actually make it like, if we substitute everything, Cs will get cancelled. It is 2 by S into Z0 Cs plus 1. Okay, now if you take the partial fraction, so it will be something like this. That will be V at a load will be 2 into 1 by S minus 1 by S plus Z0. That is 2 into 1 e power minus t by, right, where tau equal to Z0 into C. So that means at t equal to infinity, it will reach 2. So if we check the voltage here for the, that means the capacitor will be actually now charged to 2. Not to E, it will be charged to 2E. So why does it is happening? So why that is happening is because there will be reflection at this particular point, right? That due to the reflection only, this is actually happening. Okay. So at T equal to 0, the voltage is basically short circuited. That's why this voltage is basically 0. But the voltage will start build up and it will reach the maximum voltage of 2E. So I hope you understood, because these questions are very important for interview. They will ask to derive what is the, if you put a CRO here, doing surge condition or transient condition, what will be the voltage across this particular capacitor. So you can actually derive this. Okay. Now we can think about what if we actually connect an inductor. So this is the surge. I'll put something like this. And basically the transmission line. So very high frequency surge is actually coming to the inductor. Okay. So now we can actually study the model. Okay. So that is assume that this is one P, like 1 volt or 2, 1 something like unity, 1 per unit. That is basically this will become now 2, right? If you apply Thevenin, it will become 2. Then this will be having something known as Z0, and the inductor, if you convert to S domain, that will be L into S, right? So what is the voltage across this? So voltage across the inductor VL, basically 2 into Ls divided by S into Z0 plus Ls. So this is S is because if I convert this, this will be actually 2 by S, right? So that is 2L divided by Z0 plus Ls. So if you take the partial fraction, it will be 2e raised to minus t by 2e raised to minus t by just wait. So 2e raised to minus t by L by Z0. Okay. I'll write here divided by L by Z0. Okay. This is the thing, and if you draw the thing, it will be at t equal to infinity, it will go to 0. So initially the inductor will be an open circuit and it will reach to 0. Right? At t equal to infinity, it will reach to 0. Because this, when we open circuit this, what is happening is this will see 2 voltage. Right? So we have to actually terminate this, some impedance of Z0. Then what will happen? It will actually come down to 1 million. Now the a time constant will be actually depending upon these two things. So like this actually we can derive for different and different kind of a thing. And what we can think about it, something like this. So we have a surge here, right? Then Z0. Then we are terminating with a resistance of same value. This is Z0 and this is Z0, right? So we are using the same thing known as the Thevenin part. Okay, this is basically surge. Okay. Okay. Now we can convert this to Thevenin. That is basically 2 per unit. Now Z0. Right. Here also it will be Z0. Now what is the voltage across this? That will be 2 into Z0 divided by Z0 plus Z0. That is 2Z0 divided by 2Z0. 1 per unit. So whatever the surge comes here, it is actually passed through this without any amplification. So this is basically known as something known as I already mentioned, this is something known as the matched line. Matched line. So this is very important. So they will ask you to prove that in a matched line, the surge will be passed without any amplification. So you have to prove like this way. Okay, in a matched line, what happens? Okay. So I hope you understood, and we can think about another way, another thing. This is surge here. We alter 1 per unit. Then actually it is connected to a transmission line of Z0. So from here actually 2 transmission line comes. Of another one like Z1 and Z2 and comes back. Okay. So now we have to find the voltage at this particular thing. Okay. What is the voltage actually? What we see at this particular thing. So how will we find this? So we can use the same thing, right? So we can use something known as the Thevenin equivalent of this one. That is, here it will become 2, here it will become Z0. Then what happen is we will connect this. Right. This is Z1 and Z2. So we have to find the voltage across this. So that will be, if you write that one, that will be something like this. 2 is the total voltage by S into Z1 parallel Z2. That is the voltage across this particular thing. Okay, divided by Z0 plus Z1 parallel. That will be voltages at this node A. So from here actually we can find the voltage at the particular node A. Okay. These are very simple things and straightforward things. So you should remember the Thevenin equivalent part. Okay. So if you actually solve this, what you are getting is something like this. 2 into E is the voltage of the surge divided by Z1 divided by 1 by Z1 plus 1 by Z2 plus 1 by Z2. Right. So I will write in the next slide. That is 2E divided by Z1 divided by 1 by Z1 plus 1 by Z2 plus 1 by Z2. Right. Sorry, this will be 2E by Z0 because we are starting from 0, right? So if there are n such number of things are there, okay, so that will be, so voltage at if there are n such transmission lines just starting from a single point, voltage at a particular point is 2E by Z0 divided by 1 by Z0 plus 1 by Z1 plus 1 by Z2, etc. up to 1 by Z1. Okay, so this is very important. Now we can actually find something like this. So we have a surge actually coming here, E surge is coming here. Then there's a transmission line of surge impedance is at 0. Then it is actually going through n particular transmission lines. 1, 2, 3. So each having a surge impedance is at 1, is at 2, is at 3, is at 4, and then actually we can find the voltage at this particular node, or the what is the voltage actually transmitted across all the transmission lines are 2E by Z0 divided by 1 by Z0 plus 1 by Z1 plus 1 by Z2, etc. 1 by Z. Okay, We can also do the same thing like this, like the voltage across this will be the total impedance will be the parallel combination of all the impedance, right? Then multiply 2e into 2e into that particular resistance divided by that particular resistance plus Z0. At the end, you will get this particular value. Okay. So I hope you understood this one. So just write down this equation, then we can move to the next part. Okay, I hope you have written all the things. Then we can actually move to the next slide. Now we are looking at something known as lattice diagram. This is also known as Beverly lattice diagram. Or some people call this as Bond's diagram. So all the things are actually same. Okay, the meaning of everything is the same. So some people call this as lattice diagram, and some people call it Beverly lattice diagram, and some call it as Bond's diagram. So assume that there is some kind of a surge is actually coming, and this can be some kind of a termination can be happening here. So what is the voltage at this particular point, as the time progresses? Okay, at the delay time bit tau is at 0. So what is the voltage at this particular point when the time progresses? And what is the, we can, if you put something like a needle here, how will be the voltage at this particular point? So like that, if you find everything, then that is, we need to find the voltage at that any particular point at any particular time. That can be found by using lattice diagram. Okay. So for finding the lattice diagram, first we want to find what is ZL. So ZL is basically the voltage across the, the the impedance across the load. And using the ZL, we can find what is gamma L. Okay. I will be first explaining if there is only one transmission line or okay, one reflection. The more reflections will be actually what if currently 2 or 3, something like this. You can do later. Okay. So this is basically find gamma L. Then find what is the reflection coefficient here. That is basically gamma G. Okay. So for that, if this is a voltage source, then actually we will short this. Okay. So if this is a voltage source, the surge actually coming to this direction, we'll see this as a short one. Okay. Now we can actually check what happen if a one voltage step here. Okay. It is a surge. One voltage surge. Actually, what it sees in an open circuit. Okay. We can actually check here. So I will draw it in the next page. So for the forward wave, what it sees is this is the transmission line. This is the surge actually, this 1 volt is actually the surge actually coming here, and this is the open circuit, right? So what is ZL here? So ZL here is basically, if you check here, ZL is infinity, right? Because it is an open circuit. But then what is gamma L? So then gamma L will be 1, right? So here ZL is basically, it's an voltage source, right? This is for the backward wave. Okay. So this is for gamma L is basically 0. Then what is gamma G or the generator part? This will be actually minus, right? So now we can draw the Beverly lattice diagram. So for that we have to draw like this, two part. So assume that an voltage of 1 volt is actually coming, and this is having some impedance of zero. Gamma, sorry, tau. Tau is a time constant. Sorry, the delay time. So it will take one tau, one delay time. This is the time. Okay. So this is the length, sorry, and this is the time. So one time constant is actually took one time constants to reach this particular point. So this is basically one. Now it will get reflected here, right? So this will be what is the reflection coefficient? 1, right? So we'll get 1 here. Now we can look at the what is the reflection coefficient at this particular point. So that particular point reflection coefficient is basically -1, right? So now what is the time it took? It is basically 2 tau, right? So this will be -1, right? Now you check here, sorry, this is basically -1, correct? So now we can check what is actually happening here, right? So this will be, again, this will be how much it is coming here. This is 1 and this is -1, right? So this will be -1 coming here. The reflection coefficient is 1. So this will be again -1, right? Now it will come here. So what is the reflection coefficient here? That is -1. So it will be actually -1 into -1 plus 1. Here. 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. Okay, we can draw up to 5 tau at this particular voltage. So at t equal to 0 to t equal to tau, nothing has reached here, right? So that means up to tau, so up to t equal to tau, then the voltage is actually 0, right? Because at t equal to tau only the first voltage actually reached and it get reflected. That is basically 1 plus 1 equal to 2. So at t equal to 1 tau, the voltage has reached to 2 volt, right? And it stays like that for continuously. Then it reached here till 3 tau, right? It has it went to something like -1 plus -1 -2 tau, -2. So then this is actually continuously coming right there. So this is already there. 2 volt is already there. Then again this -2 is already there. So that means it will go to 0. At 3 tau it will go to 0. Right. Then again it will go to here and it will actually come back here. So at 3 to 5 tau, right? So up to 3 to 5 tau, then again it will go to, right? So this will be the voltage actually seen at this particular point. Okay. Right. So I hope you understood the thing. Now actually we can check what is the voltage actually seeing here. So at t equal to 0, the voltage is already reached. That means this is 1. So 1 volt is there. Then up to 2 tau, right? So at 2 tau, again 1 plus -1. So that is 0. So again this remains in 1, like this. So that will be the voltage at this particular point. So that is basically correct. That is the source voltage. So we have to add at all the places. Okay, so this is basically 2 volt. This is -2 volt. Then again 2 volt. Then again -2 volt, like this. So we have to add first up to tau to 3 tau. It is 2 volt. Then add -2. That will go to 0. Then add 2. So here actually we'll get 2 volt 0, 2 volt 0. Okay. So up to this particular delay time. Okay, so this is very important. So how you actually draw. Now we can check something else. Okay, you can draw this and can actually find this. Okay, so now what will be the voltage at the half of the line? Half of the line. So that means we have to find the voltage at this particular point as the time progresses. Okay, so if you check here at t equal to tau by 2, the voltage has reached here, right? So if you draw the curve, I will draw somewhere here. So at tau by 2, so till tau by 2, nothing is there, right? So it will be 0. So from tau by 2, so the next tau by 2, it will be actually, if you check here, it will take another tau by 2 time to reach here, right? So that is, this is already tau by 2, then tau, then 3 tau by 2. So up to 3 tau by 2, this will remain at 1 volt, right? At 3 tau. Then at here, what happens is it will go to 2 volt, right? So this is actually go to 2 volt at 3 tau by 2. It will go to 2 volt. Okay. Then 3 tau by 2, 2 tau, then 5 tau by 2. So 5 tau by 2, it will actually, we have to add minus 1. So it will actually go back to at 3 tau by 2, 4 tau and 5 tau by 2. So up to 5 tau by 2, it will remains at 2 volt. At 5 tau by 2, it will get subtracted with something like a minus 1. So again, it will go to 1. Then after, like, when at 7 tau by 2, something like 7 tau by 2, this will go to 0. Right. So we get some voltage like this. Right. So this is actually sum of forward voltage and backward voltage. Right. So the forward voltage is something like this, always a sine wave. Sorry, a step wave, and backward voltage is something like reflected kind of thing. So at every point, all these things are actually superimposed, okay, to get the particular value of voltage. So this will be actually repeated. Similarly, we can find 3/4 of the line, like something like 1/4 of the line, like this. Okay. So these are actually very important part. So we can do a numerical one and you will get understood. So we assume that ZL equal to, sorry, surge is actually coming here of 1 volt. Then here the gamma L is 1 and gamma G is 1. Okay. Right. So we can draw the thing. We can take something like 2 milliseconds. Okay. It's the time to reach from here to here. So millisecond is a very large time, but for the time being, we can actually take, okay, or we can take 2 per unit time. Okay. That will be nanosecond or microsecond, so whatever, 2 per unit time. Okay. So that means at 2 per unit, this will reach here, 1 volt is here, so we'll go to 1 plus 1, 2, right? So at 2 per unit time, our voltage is basically 1 plus 1. Now here, like so, this is 1 per unit time. 1 per, because the delay time is sorry, delay time is 2 per unit, right? So delay time is basically 2 per unit. Then it will reach here, like again 2 per unit it will take. That is 4 per unit. Now it will reach here, something like 6 per unit. It will reach here, something 8 per unit. It will reach here, something like 10 per unit. Okay. So one here also it will be like here also gamma g is also 1. So 1, 1, 1, 1, 1, right? Because everywhere it is 1. Now we can find this. So if you draw our line, 2 per unit, 4 per unit, 6 per unit, 8 per unit, 10. Now up to 2 per unit, there is no voltage, right? So 2 per unit, it is 0. Then at 2 per unit, what happens is 1 plus 1, 2 will happen. Right? So basically at 2 volt is actually coming here, 2 per unit voltage. Okay? So at 2 per unit time, we are getting something like 2 volt. Then it continues to stay till 6 per unit, because the next surge is coming at the 6 per unit time. So it continues to stay till 6 per unit time. And at 6 per unit time, what happening is this 2 per unit is already there, because the surge is actually continuously coming. Okay, this is not a pulse. And plus this 6 per unit, 2 per unit is already there. So it will become 4 per unit. Right. Right. So this will stay up to 6, 8, 10. 10 per unit. Right. This will be the voltage at this particular point. Now we can check what is the voltage at this particular point. Similarly to, okay. At t equal to 0, we are getting 1 per unit, right? It will stay up to 4 per unit. Then 8 per unit. So it will stay up to 4 per unit. Right, 1 out. So at 4 per unit, what is happening is this 1 volt already there, plus 2 volt is coming. So that is basically 3 volt. So that will stay up to 8 per unit. So at 8 per unit, what happens is again 2 will come. So that is basically 5. That is basically 5. 6, 2, 4. At 10 per unit, it will become 6. Right. So if you check here, you can see some wonderful things actually happening here. So the 1 per unit is actually here, coming there. So there is some, like time delays there to appear the voltage in the neutral end. Okay, that is a delay time. So 1 per unit is already here, and it takes 1 time 2 per unit to reach the voltage at this particular point. Then actually it is going 6. Okay, so so what is the voltage at 4 per unit in the line end? So the voltage at the 4 per unit, sorry, the neutral end. So voltage at the 4 per unit is actually 2 volt here. So if you check the 4 per unit, it is actually something like a 3 volt here, because here is the higher voltage, and this will be actually traveling to this particular. Okay, that's it. Now we can check what is happening at the middle of the line, how the voltage is varying. So you can draw it here. So up to 1 per unit, there is no voltage, right? So that is half of the time. Up to 1 per unit, what happens is 1 volt is actually coming. 1. Then 2 per unit is happening here. Then 3 per unit, what is happening is again 1 volt is coming. So at 3 per unit, so up to 3 per unit, this 1 volt remains same. Then at 3 per unit, 1 volt will also come. That is basically 2 volt. Then 3, 4, 5. 5 again 1 volt is coming. So at 5 per unit, this will actually go to 3. Right. At 7 per unit, it will go to 4. At 9 per unit, it will go to 5. Right. So that 5 is there, and after that, actually you can see the increasing going to happen. Okay. So this is how we have to use the Beverly lattice diagram for finding the voltage at the line and outer line. Okay. So now an obvious question will be coming, how can you say that the voltage is doubled here, right? So in our case, what we are seeing is, this is a circuit. If you look at from here to here, what we see is this voltage, right? So that is happening only for a lumped system, right? For distributed system is different because, so assume that he is a 50 hertz. That means the wavelength is very, very large, right? Something like kilometers, and this is in something like some centimeters. That means, whenever you look at this, you can see only the some part of the voltage, right? That also remains a constant. So at this particular part only you can see, right? Only this particular, and always remains a constant, and that is basically what you see. So, but if you give very, very large frequency thing, then there is 2 or 3 or 4 waves actually coming here. So you can see the complete this reflection and refraction actually happening, transmission actually happening here. Okay. So by this, it's almost 57 minutes. We will stop the class here, and tomorrow in the next class we will be continuing looking at this transients part a bit. Then this is the most important part of power system, like one of the most important part of power system analysis. So after that, we will look at the load flow and economic dispatch. Okay. So by this, then the power system analysis part will be completed. Then we will go to fault analysis and other kind of things. Okay. So I think next class also we will be looking at least the half of the class we will be looking at doing some problems related to this, because this is very important and a lot of places they will ask for the interview part. Okay. So I hope you understand these things, because like most of the places they won't teach you how to do this. A lot of things known as Bergeron's method is there. Then there is something known as positive slope, negative slope kind of a thing is there. Then there are a lot of methods to find this. Is something else, analytical method is also already there to find this, because this is actually coming from an analytical method. If you look at the one of the famous book by Beverly, the traveling wave phenomena in transmission systems. It's a 1931 book. Okay, so if I want, I can write you the name. It's a very, very, very old book. The traveling wave phenomena in transmission systems. Traveling wave phenomena in transmission system. If you look at this book by Beverly, you can actually see an analytical method for finding this. So he has deduced this from that analytical method. Okay, that's why this is not a Beverly lattice diagram or a bounce diagram. Okay. So that's why you have, it's a very good book. If you want, we can read. He has introduced a lot of new concepts, like at that time, something known as Duhamel's integral theorem, Duhamel's theorem, then response to lightning surge, response switching surge. So everything he has covered in this particular book. So these books, I don't think this is available in, you can buy it or not, but this is available in, I think, in archives. Okay, so the Wikipedia or some archives is there. You can download the book from there. I think it's a free download book. It's a very, very old book, and you can see, I don't say that you should read the complete book. If you want, if you are if you are enthusiastic to study the core electrical thing, what is actually happening, you can read this book as a reference. Okay, it's a very good book, and he has covered a lot of things about transmission lines, traveling waves, standing waves, how the things can be solved, and all these things. Okay, just a reference. If you want to read, you can read. Normally people just study this and they don't know how these things are coming. So how these things comes, you can see in this book. It's a very good book, and something like a mind blowing. Okay, bye, and we can actually see in the next session where we will be continuing discussion the transients. Thank you.